Okay, I should start by putting these activities in context. 60 years ago, on April 17, Jose Adem and Sam Gittler, two iconic figures in Mexican mathematics, launched the mathematics department at the newly created Research Center in Sciences, the Centro, as it was known worldwide soon. And to celebrate the occasion, we have set off a series of talks by high caliber mathematicians in the world. So without further ado, I will let Jose Perea to take over and introduce our speaker today.
Good morning. It is a pleasure to introduce the first speaker this morning, Gunnar Carlsson, who almost doesn't need any introductions, but we're going to do them anyway. Gunnar is currently an emeritus professor at Stanford University, where he held the Anne and Bill Swindells professorship for many years. He's made deep contributions to equivariant homotopy theory, algebraic K-theory, notably proving Siegel-Burnside conjecture. He's now regarded as one of the founding fathers of applied and computational topology, not only sort of proving many of the results that enabled us to apply these things in practice, but also organizing talks, educating young researchers, and popularizing the subject by giving many talks like the one he's giving today. So without further ado, Gunnar, please take the floor.
Okay, well, thank you very much. It's really an honor to be part of this celebration, and I want to thank the organizers for inviting me. What I want to talk about today are topological methods for deep learning. Deep learning it's a very interesting subject, very powerful. It's kind of solving many different problems, and I think it affords a huge opportunity for mathematicians and in particular for topologists to work on it. So, let's see here. What is the problem? Oh, there we go. Okay, so okay, there we go. So the first question is, what is deep learning? So deep learning is a methodology. It's based on neural networks, which are computation graphs. They're directed graphs, and we'll talk a bit about them. It has produced outstanding classification results for complex data. So, for example, a complex data type might be images, and you might have a data set that consists of digits, hand-drawn digits, and the machine then gets, classifies the zeros from the ones from the twos and so forth. It also has been applied to text, which is a very powerful thing. Very recently, some great stuff has come out of Google on that, and molecules, which is work done by Guo Wei at Michigan State. There are, however, some problems with it. There are sometimes adversarial examples. So, for example, when this method is used in autonomous vehicles, the following sort of thing can happen. You would obviously need something which can read speed limit signs. And what you find is that if you do it, when you will often run into the following problem. If there is a speed limit sign where it's supposed to read 35, but the middle prong is a little too long, it will get read as an 85 instead, which is an obvious problem from the point of view of the vehicle and of the driving. There's a general lack of transparency. The method, it's not fully understood, or I would say we have only a superficial understanding of how it works. It's based on certain optimization methods, but nevertheless, it has those issues. And what that does is that general lack of transparency, the fact that it's viewed as a black box limits its usefulness in many key domains, such as financial regulation and healthcare. And we'd also like to be able to learn more complex models, what's called representation learning. Okay, so what are they? So neural networks are an attempt to model what goes on in the human or the mammalian brain, where you have neurons and they are connected to each other by edges. Here is an abstract version of a particularly simple kind of neural network. This is called a feed-forward neural network. So here, think of the dots or the nodes here as neurons, and then think of the edges as connections. So in this case, you can see the neural network is broken up into some layers, and you feed from one layer forward to the next layer, hence the name feed forward. And the way that you operate here is that you assign numbers. So a state of this machine, think of it as a machine. A state is an assignment of numbers to each node. And so what you can do here is, if I have an input set of values for the input, I can then compute the values at the next layer via a formula. So, and the formula should involve only the edges coming in. So in this case, now this is called fully connected, because what you'll notice is that every node is connected to every node in the preceding layer. But we'll see more complex things here in a minute. But in any case, this is an example, and you know, the particular formulas that are involved are called the activation functions. So here's the story. Given a data set and an output function that we have, perhaps Boolean valued, or you know, maybe multiple classifications, or even numerical continuous. So weights are assigned to the directed edges of the network. So this is the way that one works with the network, is you assign a weight to each one of these edges. And that is an entry, a coefficient in the formula that evaluates the node, this node, say right here, in terms of these three. So there's a variable formula in here with weights. The activation at the node is then computed using a uniform function of the activations of the nodes connected to it. And then it's trained by optimization algorithms acting on a set of weights. So one actually takes these weights and actually, you know, does a form of gradient descent on them, so as to optimize the fit. So the thing that's being optimized here is the loss function, or the error between the output function and the computed function. So the final output is a certain kind of formula, but it's very, very large, because it involves a coefficient for every edge here. So you can see this is going to be a very large formula. And this, by the way, is just sort of a toy version. The real thing is much too large to put on the screen. Now, convolutional neural networks are a specialized version of this notion. So, but they are designed to address specific data types. So images, which would be 2D rectangular arrays, text or time series, which would be 1D arrays. And so here's the one for images. So the idea here is you still have a feed forward network, but what you have now is you have a geometry on each of these layers. So you notice that the input layer here is an image, 24 by 24 image, and so the features, the coefficients here are pixels. But those pixels are arranged in a geometry. They're not just flat, you know, pixels with no structure to them. They are actually arranged in such a way that I know which pixels are far apart from which other pixels, and it's this grid geometry. And in fact, all of following layers are also grid geometries. What you'll notice is that it's not, the second layer is not a single grid geometry, but multiple such grids. And that's an important thing, which we'll come to here in a minute. But the key point is that, you know, the connections are now not general. So for example, if I'm looking here and I have a pixel down in this left-hand corner here, it is not connected to the pixel in the upper right. What you do is you take instead every pixel in here is connected only to the pixels in here that lie nearby within some square neighborhood, maybe a 3 by 3 or a 5 by 5 neighborhood. Okay, let me say, so now there's an additional condition here, which is the following. So, and it's the reason for the name, the convolutional neural networks. So there's, in addition to having just this sparser connections, it's also the case that if I find that I'm detecting, say, a dog down in this area here, and but I have another dog up here, it should be detected in exactly the same way. And what that means is that if I take one of these grids here, one of these convolutional layers, and look at it, the connections at this point to this point are exactly the same as from this point to that point. So the weights have this convolutional property that they are supposed to be the same as I move throughout this image, and compute its coefficient in this one. Now, of course, the weights can change as I move into these other grids. Then I have different ones. But within a particular pair of grids here, it is insisted that there's a single collection of weights that gets computed. And that's very powerful because you want to insist that you would learn or you would detect something in the same way everywhere in an image. You wouldn't want to detect it in different ways. Okay, so now here's the question. Does learning by CNNs behave like human learning? So what do we want to know? Can we see similarities to what we found in image patch data? And I'll talk about the image patch data here in a minute. What happens as the network learns? So we might ask, you see, what happens to the what happens to the weights as I apply the optimization algorithm and run many steps of the gradient descent algorithm? What are the responsibilities of the various layers? What do they capture? Okay, and so what I want to tell you about real quickly is some analysis that we did, and we're going to use this to sort of check against what we find in the neural network. So one of the very first things we did in starting to develop topological data analysis was the analysis of a data set of 3x3 patches in natural images. So this was joint work with Vin De Silva, Tigran Ishkanov, and Afroz Omarodian. So we studied this data set of 3x3 patches. It was constructed by David Mumford and collaborators. And they constructed a data set of high variance patches, that is to say, patches where significant change occurs within the patch, so it's not constant. Obviously, if I'm trying to do statistics of natural images, which is what we're trying to do here, then I wouldn't want to retain the constant patches. They would dominate the statistics, and they're not very interesting. And what we do is we study only the densest such patches. So we're going to take these the high variance patches, and among them compute proxies for density and threshold by that, so that we'll find only the most frequently occurring motifs. And this is motivated by the goal of understanding how the tuning of neurons in the visual cortex is affected by statistics of natural images. The reason is that what you expect in a device like the primary visual cortex, which is the next level beyond the retina in the visual pathway, what you would expect is that if you have a frequently occurring pattern, you would want to detect that pattern with a very small number of bits. And so maybe even an individual neuron. Can you tune an individual neuron to capture something that occurs frequently? Okay. And so here's what we found initially. You can see here that the most frequently occurring stuff, the densest stuff that's occurring, is precisely organized in a circle like this. It's a discretized version of a linear gradient going from black to white, but at different angles. And this is perhaps not so surprising. This is using one non-local density measure of, a density measure that counts points in a rather large region of the data set to estimate density. But what this basically says is, linear approximation is good. The first thing that you might expect is linear. And frankly, when we did this, we thought, okay, that's interesting enough. Let's just check that the result is robust. We want to see that, and so let's change to a more local density measure, one which estimates density using a smaller neighborhood around a point. And what you get then, though, we were quite surprised to find that we did not get just that single circle. That's one that it still exists, and we'll call it the primary circle here. But that there are actually two other relatively high density things that occur. And so what we see there are the two secondary, that we call two secondary circles. You'll notice that they connect up with the primary circle. So in that lower left here, the red here is the same as that red, and this red is the same as that red, and this green is the same as this one, and so forth. So this is actually a three-circle model. These are three things, and they're hooked together. So that turns out to be what the high density thing with a more refined density estimator. And Now, it turns out then that if you relax that density threshold a bit, you can get something which is even, which is two-dimensional, and it's called a Klein Bottle. And so here, what you can see is that, and I've just drawn the patches as kind of circular for simplicity here. What you can see is that these patches are actually arranged in a rectangular array. You can see here, this thing here, followed by this, is the primary circle. And then the two vertical yellow and green lines are the two secondary circles. But now there are additional ones. There's some secondary circles at a 45-degree angle, say, in here, and at 135. Notice, though, that what happens is that this point over here is identified not with this one, but with the one in the lower right. So there's actually an identification going on with a twist where, this point is identified with this point, but also this point is identified with this one, no twist in the vertical direction. So this is an object, when I make those identifications, that's called the Klein Bottle. It's something that you can start to get a handle on by making a Möbius band out of paper, as many of you may have done. But then you want to try to impose additional identifications of that edge as you try to close it up. And what you find when you do that is that you end up tearing the Klein Bottle because it does not fit in three-dimensional space. It needs 4 dimensions. Okay, so that's the object that we found. That Klein Bottle is is a key object. It's kind of gives, if you like, some particular quadratic kind of patches. So the primary visual cortex now is the lowest level processing beyond the retina. There are higher levels that perform more abstract tasks. The lowest level is like edge detection and line detection, and then there are more abstract tasks that might include more complex objects. But Hubel and Wiesel showed that individual neurons are tuned to detect edges and lines. So this is consistent with the idea of compression of frequently occurring signals, as I mentioned. So our statistical analysis is entirely consistent with what they found, which is that the primary visual cortex captures edges and lines. And here's just a picture of it. As you can see, you've got the V1, which is the visual field down at the bottom, but then you have the more complex things as you get higher up, faces, objects, and so on. Okay. Okay, so sorry about the typo there. Data has shape and the shape matters. I'm going to tell you a bit about topological data analysis. So when we think about data, many of the tasks that we use to analyze it, like linear regression and clustering, are actually about the identification of the shape of the data. So for example, when I do linear regression, I have a data set like the one that I showed you here, this one. It fits very nicely with a line. It can be well approximated with a line. And so I would do linear regression to it. On the other hand, a data set like this doesn't really fit with a linear regression model. It instead fits with a clustering model. And the clustering can be thought of as, instead of as approximating by a line, instead approximating by a discrete set of 3 points, or however many points are involved. So we're talking again, clustering and regression are both methods of approximating data by shapes. But what about if I have this? This might occur with time series where I have periodic or recurrent behavior. In this case, neither of the preceding two work, but a loop does. And now as mathematicians, we could say, great, we're going to build a loop detector. And we could certainly do that. In fact, there has been some work on explicitly that, but we might also worry a little bit because we might say, we don't really expect that the next data set we get, it's not necessarily going to fit with any of these 3. It might be a 4th thing like this one, which is a letter Y. And here, I could build a Y detector or call it flared. I could also detect these things. But at this point, I'm really worried. I want to say, I don't want to have to enumerate all the possible shapes because there are too many. I don't want to have to build a method, de novo for each one. So instead, what I want to do is I want to build a method for data analysis that actually captures all shapes all at once. And that is what we would call, topology. It is building approximations that are graphs or simplicial complexes instead. Now, this was initially, the first paper in this direction was in 1736 by Leonhard Euler, trying to solve the Königsberg Bridge problem, which the question was, could you cross all the 7 bridges crossing the River Pregel in Königsberg without crossing any bridge twice? And there's a lot of complexity in this data, as you can see. But what he observed, for example, the breadth of the river, the size of the islands, the length of the bridges, and so on. What Euler observed, though, was that there's a simplified version, which you can see there on the left, which is a network which describes the model. So this is a graphical model that he built that captures the phenomena on the right. And from looking at this simplified picture, it was easy for him to determine that the solution was that no, you could not. Okay, so what I want to now show you is how to do something similar systematically for data. So suppose that I have a data set like this, and I have a projection of the data set. So, and this projection, it might be, as here it's the y coordinate function, but more realistically, I tend to use statistically meaningful things like density and measures of centrality. And also I might use more than one, but we'll use just one projection here to give an indication of what's going on. So we're going to use that projection to bin the data into overlapping bins. So you can see here, I've actually taken overlapping intervals on the line and covered it by that, and then taken their pre-images. And so what I now get is I get 4 bins. And you can see that they overlap because those orange parts in the top are also the same as the orange parts in the second from the top, and so forth. So now what we'll do is we'll cluster each bin using a fixed clustering method. And you can use whatever clustering method that you want here, but you'll notice that the second and third layers here break into 2 clusters, whereas the top and the bottom layers each break up into a single cluster. So now I've got this clustering, and it's what I would call a soft clustering because the clusters overlap. And what it does is it forms a covering of the data set. And so each of these clusters, or what I would call partial clusters, because they come from bins rather than the whole thing. The fact that I have this, that it's a soft clustering means that I have some geometric information, namely which clusters overlap with each of the other clusters. And so I can draw edges between them. And now I have built a graph or a simplicial complex. And you'll notice that it gives a reasonable model for the original data set, which was a circle. We've lost some information about curvature and so on, but oftentimes we don't care about that. It goes along with Euler's philosophy of kind of simplify away some of the detail to give you the overall structure. Okay, so topological modeling. I would argue that it's a method, new method for mathematical modeling. Typically, if one thinks of mathematical modeling, you think of equations, maybe differential equations, but the model output is a network, not equations. So in this case, and this is a flexible method, a very flexible method of modeling. It's also not just visualization, because the model actually has a lot of functionality, has many capabilities. For example, if I lay the graph out on on the screen, I can select with the mouse a region of the network, and that will select for me a subset of the data set. So I can study subsets, subpopulations of the data set because I have the overall organization here. I can also do segmentation, break it up into non-overlapping segments. I can color by quantities of interest, such as, for example, if it's a business data set, I could color by revenue, or if it's a life sciences data set, I could color by survival. And get kind of hotspot analysis, find out where in my data there are hotspots for these particular covariates. I can explain groups, that is to say, I can take 2 groups and use methods like a Kolmogorov-Smirnov method, for example, to determine what are the variables that most effectively distinguish between the 2 groups. And it turns out I can build feature creation and selection also. Model assessment and improvement. Oftentimes I have some models like linear regression models or logistic regression models, and they work pretty well, but maybe there are some systematic areas where they are going wrong, and it would be interesting to know about those. Okay, So what I want to now, I want to return to the original goal of this work, which was to show you what's the topological analysis of the weight spaces. So what are the weight spaces? Well, if you remember from that convolutional neural network, we said that attached to every grid in the first layer and every grid in the second layer, there is a single collection of weights. And what that is, because I connect every node with its 9 nearby nodes, I actually get a 9 vector. Each of those weights can be colored by a grayscale value. So I have data that's of exactly the same type as the 3x3 patch space that we studied, because 3x3 patches in natural images are also, have 9 grayscale values arranged in a rectangle. So in this case, what I can do is I can now say, let me do an analysis, run many times a study on a particular data set, which is MNIST, it's a data set of images. And I can ask, what happens, what those weight configurations, how do they cluster? How do they look? And the answer is here that you can see that they form a circle. And in fact, the circle, the points, if you like, or the weight vectors, which are pictured around there, are very similar to the ones that we found in the natural image data. So that's very striking in my view. It shows that the training is doing the same thing as what was being done in training the primary visual cortex that was done in the biology of training it. Now, you might say to me, if you look at this, yes, okay, so you fiddled with this model, maybe you just made it work out this way. And so on the right here, I want to convince you that that's not the case. So it turns out there are methods from topology called persistent homology that actually measure the presence of loops and connected components. And they measure them by saying, there's a loop present if there's a long bar in a certain barcode. So what you're seeing on the right here are the 2 barcodes for dimension 0 and dimension 1. And you can see that there's a long bar in dimension 0, a single long bar, which says that, oh yes, the space is connected. And then the fingerprint in dimension 1, there's a long bar, and that suggests the presence of a single loop. So this is sort of a simple way of measuring what's going on inside there that is independent of this model, which we call a mapper model that's on the left. But the mapper model shows you what's going on, and then confirming that it is an accurate representation of the data is what the persistent homology does. Now, the other question we asked is what's going on during learning? So here, what you can see is this is a simple one. This is a 2-layer network. In fact, all the networks that we used here are 2-layer networks. And the mapper models here, let's look at the first row, which is the first layer. So you can see initially it's kind of random. It's actually a carpet. But what you can, the coloring is being done by coloring by the number of data points in that particular node. So each node here consists of a collection of data points. It's one of those clusters in one of the bins that we saw before. And so now, as I move over to the right to one, you can see that they are sort of concentrating around the boundary. And as I move to the next step over, you can see that I'm actually producing the loop. So you can see how the loop is being created here. All right, so that's a good thing. But now something non-intuitive happens. The loop starts to degrade here. You can see it's filling in. And ultimately, it concentrates around 4 corner points and then something in the middle, which ultimately looks kind of like a bullseye. Okay, so what happened here? We would have expected it to stop here. Well, here's what happened. And this, by the way, is just because we believe this is because we have only a 2-layer network. I'll show you one which behaves more intuitively here in a minute. But what you'll notice here is that the second layer is behaving, not much is happening until about here. As this one is starting to degrade, what you can see is that the points in the second layer are starting to concentrate around the boundary and starting to create the primary circle around here. So it's kind of taking up the responsibility of that primary circle that has been, abdicated by the first layer. So as again, I think this is an anomalous thing because we're dealing with a 2-layer network. But here's another situation where we're using a more complicated data set called CFAR10, which has many more classes in it, more digits and so forth. And here you can see that the actual three-circle model even appears. This is at the first layer, which is with looser density thresholding, more localized density estimator, and so on. And again, the fingerprint for the three-circle model is 5 bars, which is the 5 bars that you see here. And again, it's connected. And here is a much more complex network, a much deeper network called VGG16. And in this case, what we have found here is that the lower layers contain only primary circle kind of stuff, and then the higher layers you start to get some more complex things coming from the secondary circles. And now you get here in layer 5, you get something even more complex, which would go beyond the primary visual cortex, which is this crossing. Here you have crossings and bullseyes. And you can see anyway how the responsibilities of the various layers are arranged. But notice in this case, each layer has within it a primary circle. It's always using that, but then the responsibilities for detecting bullseyes and crossings are distributed. Okay, so now the question is, can we make use of this information somehow? Well, one thing we could do is we could say, look, the neural network seems to always be learning this primary circle, and maybe even the Klein bottle or the three-circle model. And so one thing that one can do is to hard code it, is to actually hard code the primary circle and the Klein bottle. And what that permits is both the speed up and generalization. It speeds up the learning, a speed up of about 2x for MNIST and 3.5x for a more complicated digit data set called SVHN, which consists of house numbers. An interesting feature about the deep learning is that if I train on MNIST, if I train a model on one data set of digits and evaluate it on a second one, say SVHN, what I actually get is 10% accuracy on a 10-way classification problem. So, the learning that's been done, that's done in training on MNIST is training on particular features of MNIST and doesn't allow it to generalize to other data sets. What we find is that when we hard code the primary circle and Klein bottle, not only do we speed up the learning and therefore get to learn on less data, we're also able to generalize better. So now we get to 22%. And next we'll show you more dramatic improvements using better methods here in a minute. But in any case, the point is that this kind of hard coding of the primary circle and Klein bottle allows you to improve on these properties of speed of learning and generalization. Okay, so I want to talk now about topological data analysis and deep architectures. So convolutional neural nets, they use a grid structure on the set of pixels in a critical way. So the pixels are the features for image data sets, right? So we use this a priori geometry and we use it in designing the neural net. This is important in restricting the classes of formulas that are considered. So you don't want to have the learner to have to go through too large a class of formulas, because it means the optimization, it's sort of problematic anyway. There are lots of local minima for the optimizations. And so you want to restrict the class of formulas that are considered. So we can restrict them to formulas that are local in the geometry of the feature space. So the thought experiment says, yeah, with time series, you probably learn derivatives. With images, you learn directional derivatives. What if there is no a priori geometry? So we have discovered geometries. We have discovered feature sets that carry geometry, the primary circle, the Klein bottle, etc. We can use the geometry to design architectures. Okay. So now I want to talk about something which I think is quite powerful here and quite general, actually. So this is what we call feature space modeling. So suppose that I have a data matrix. So oftentimes data is given as a matrix where the data points are the rows and the columns are the so-called features. The coordinates, if you like, of the data set. Now, what we've shown is, what we do with the mapper model that I described is oftentimes we produce models of the row space, but we can also consider the transpose matrix and build a topological model of the features instead. And when there are many features, it's very useful to create these topological models because they are compressed versions, if you like, keeping track of some geometry. And it compresses and recognizes correlations among the features. So each row of the original matrix gives a function on the feature set. Now, so think about it for a second. If I have a data matrix and I have a data point, it produces a function on the set of features. And so it means that every data set can be viewed as a function space in some sense, or as a set of functions. And so I want to show you how this works. So here was an analysis that we did using the mapper method on breast cancer. This is the so-called NKI data set, one of the benchmark data sets for breast cancer. Well, probably nowadays it's been superseded, but this is 10 years ago, 15. And you can see what we found here is that there were three real cohorts. There's one called cohort A down at the bottom right, which turned out to have perfect survival. In fact, it's about 8.5% of the data set, and it has perfect survival. And let me say, this model uses no information about survival, or in fact, any clinical information at all. It only uses so-called microarray data information, so messenger RNA expression levels. If you don't know what that is, don't worry about it. It's something that one computes on a sample, and they're complicated numbers. There's about 1,500 of them for this particular situation. And so now what you see is there's also a cohort B on the upper right, which is a much more, unhappy diagnosis or unhappy prognosis. It includes the triple negative breast cancer, which are very difficult to treat. And then there's cohort C on the right here, which is kind of something, appears to be something in between, not nearly as well understood. Now, what I'm going to show you in a second here is the fact that we're going to take those 1,500 features and build a mapper model of them, and then color them by the different cohorts. So each cohort, by taking averages, will produce a function on the feature space, and we'll show you what that function is. So here I now have noticed I've got the graphs. The topological models are all the same. The complexes are all the same. But the colorings are wildly different for the different cohorts. So for cohort A there, you can see that I've got something which is, bright blue down here, under-regulated, and up here, over-regulated. In cohort B, that's completely reversed. It's bright red down here, whereas it's blue over here, it's blue up here, except notice that here, and even over in this cohort, there are certain of these genes that are certain elements which don't change at all. So one might think of those as sort of anchor genes. And then cohort C, as we look at it, it looks more like a weak version of cohort B than it does like cohort A, which suggests that in our thinking about this, that we should realize that the cohort A, which is the high survival one, is perhaps the exceptional one, the one that has some kind of very strong response that enables it to respond to the cancer, whereas the other two do not. But notice that how much information is contained in this. In other words, it's not just, as one would ordinarily do here, one would list the 1,500 genes and order them by so-called p-values, for survival. Here, one gets a picture of it, a picture of what's going on, into immediately understanding that, well, there are two things going on. There's a region here which is under-regulating, region which is over-regulating, and then also this additional curious piece of information about the presence of some anchor genes. So there's the potential for obtaining much more information this way. And I'll show you another example from the so-called from the Larry Smarr group at UC San Diego. This is from the gut biome. So they have sampled material from human gut biomes from people suffering from ulcerative colitis, healthy people, but also Crohn's disease. So what you can see here on the lower left is the healthy space. So in this case, I should say the features consist of 10,000 bacterial subpopulations. And so the features are actually abundances of those populations. And so what you can see here is that the healthy is colored a certain way. If you look on the right here, I get the coloring looks very similar, except you'll notice that in this case, there's a circled black region here, which has no counterpart over here. And so it looks like it's just these guys, the particular bacterial subpopulations corresponding to the elements that are in that circled red thing that are characteristic of the ulcerative colitis. And similarly here with Crohn's disease, you can see that what happens with Crohn's is it looks pretty much like the healthy, except it's missing this circled area up here. So it doesn't have the bright red up there. So again, sort of a very quick way to get at it. And this is characteristic of a lot of life sciences data where it isn't, a single variable that's acting, but it's actually a bunch of variables, a collection of a population of features that's acting. And this kind of immediately calls out those subpopulations of the set of features. Okay, so now having talked about that, I want to now give a notion of what one could talk about as generalized convolutional neural nets. These are what would be called graph-based convolutional neural nets. So a general feed-forward structure here, by that I would mean a collection of sets, and then a correspondence, if you like, or a relation between the I minus first one and the ith one. So that's what we would call sort of an abstract version of a feed-forward structure. So such data can be used to create a network, because what I would do is I would build the nodes. These are all the elements in all the xi's. So each xi is a layer, and I will simply draw an edge from anything in xi to anything in xi plus 1, which is contained inside that correspondence or relation. So anyway, the correspondence determines the connections from xi minus 1 to xi. And, geometrically, oftentimes I can build, relations or correspondences that depend on geometries, as we'll see. So here, for example, if I were to take my feature space, so my feature space here would be a Klein Bottle. This is a useful feature space in the case of images, because for each one of these, there's a patch. And if I can then take a 3x3 patch and dot it against that, that gives me a number, so that I can actually take an image and create from it a function on the Klein Bottle. So if I should say, yeah, any image will create a function on the Klein Bottle, or I should say any image patch even. And so what that suggests is that this kind of picture right here, where I draw a neural network where I have each layer is organized into a Klein Bottle, and I draw the connections here to be local within that Klein Bottle. Okay. So now what I want to do is I want to talk a little bit about some experiments with these things. Okay, so here is, we have now built some of these neural networks based on the Klein features and also based on the primary circle features. And so what we're talking about here is a generalization. So we're going to take MNIST itself, which is a particularly simple data set. And what we're going to do is we're going to create a noisy version of it by adding Gaussian noise to it. And now there are 5 separate models that we tried here. There's the blue one, which is a standard neural net. And then there are 2 versions of the Klein, which are orange and green. And there are 2 versions of the circular, which are the purple and the red. And so what we ask then is, say that I train on the noisy MNIST and evaluate on the clean MNIST, the original MNIST. Then what I get in terms of the accuracy, and you can see this is after a certain number of after it's seen a certain number of images. So the bottom row there is the number of images, and so what we find is that you can see that the yellow, the orange, and the green, learn very, very rapidly, get to something that is pretty accurate, 0.8, 80% accuracy. You'll notice then that it drops off a little bit, which is interesting. This is this well understood aspect of deep learning, which is that it will drop off after a while because the learning or I should say the loss function, is done based on the accuracy on a test set. So it's measuring something about overfitting. And so you start to have some overfitting, which is then making this thing drop off in its evaluation. What you can also see is that the circle ones, they also get to a good place, but they start to drop off also. The circle ones are the purple and the red. The ordinary neural net, however, doesn't do anything here. So this points out what the value is in pre-training on these features. I say in hard coding the Klein Bottle features and the circle features. And we similarly did the same thing with training on the clean data set and the testing on the noisy one. And you can see on the right here, you get the same kind of thing. That the Klein features clearly do the best. They get very rapidly where they need to go, whereas the others don't. And here is another situation where we're talking about training on MNIST and evaluating on SVHN, which is another data set, and vice versa. Again, here, obviously, you don't do as well, although what we managed to do was to get to roughly about 35% accuracy in generalizing from MNIST to SVHN. So MNIST here is the simpler data set. As you'll notice, SVHN, if you train on SVHN, you do better, you get up to close to 50% on MNIST that way. And this is another example of that. Here are the learning rates that one can see. So again, with MNIST itself, there's not that much difference, but with SVHN, you get something that learns quite rapidly compared to an ordinary neural net. And US Postal Service is another one. So here, this includes one version of the circle and one version of the Klein. Now, this was the most dramatic one for us. So this is learning on the so-called UCF video classification challenge, or video classification problem. So this is a data set consisting of videos taken by of humans performing various kind of actions, walking, running, maybe biking, and so forth. And learning video is very, very much a harder problem than static images. As you can imagine, the dimension, adding that additional dimension makes it that much bigger, but it's also much more complex what can happen in there. And it's so complex, in fact, that almost all the methods for learning on this data set, for learning this classification problem, involve using a lot of other data, other video data, and training on it, so that one trains up and then do what's called transfer learning, where I transfer that in, and then I can train on and do fairly well. However, what we wanted to do was to say, we don't want to train on any other video data. We don't want these large amounts of other data to be required. We're going to train exclusively on the UCF data set itself, not on other video data sets. And so what we did here is, now you say video, what I've been talking about are features based on a Klein Bottle that get used in studying static images. The corresponding gadget for video turns out to be an object called the tangent bundle to the Klein Bottle. So we use that as a feature space. And what we find is that when compared with the standard approach with a standard 3D neural net, this is what we achieve. So we're able to get to a better place, and where an ordinary neural net never gets there, and we get there quite much, very, very rapidly as well. So this kind of dramatically improves the learning over a standard neural net, and a standard convolutional neural net. Now, I should say, the interesting thing about this is that it's plugged into a 12-layer ResNet, which I won't go into the details of that, but the point about this method is that it's something that can get plugged in anywhere. So there are lots of methodologies out there now for studying various deep learning problems. There are so-called transformer networks, which use notions of attention. There's ResNets, there's recurrent neural networks, on and on, lots of methods. All of them can accept the plugging in of a Klein thing or a tangent bundle to the Klein thing, whatever, into them and get improvement that way. So it goes back to sometimes we talk about this as the BASF approach. So BASF is a German chemical company. I believe they're still around, but they used to market themselves and say, we don't build anything that's in your house. We don't build any of the whole things, but we make everything in your house better. And so the idea that you should be able to plug in like this is a very useful thing. And to give you a sense of what I mean, Gary Marcus was the head of artificial intelligence at Uber. He's since left then and gone back into academia and maybe started his own company. But he's written what he called a friendly critique of deep learning. And he said the following. He said, deep learning is data hungry. It requires a lot of data to learn. And oftentimes that's a huge problem. That's a huge, the ability to collect a lot of labeled data is really, creates a lot of difficulties. It also has trouble working with prior knowledge. Supposing that you know something, supposing that you know the fact that we had, for example, the Hubel and Wiesel result, where you know that the primary visual cortex is training on lines and edges. Well, you should be able to plug that in a systematic way and get better performance, so that you can really incorporate the prior knowledge in an effective and useful way. It has trouble with generalization, as we've seen in adversarial examples. The standard model for the neural net, absolutely got nowhere with the generalization. And the ability to put in some kind of prior knowledge helps to a great degree with that generalization and the corresponding problem of the adversarial examples that I mentioned. And he summarizes that by saying, the trouble with deep learning is that we're not yet at a point where it can be engineered. That is to say, what we mean by engineering is sort of an iterative process where you gradually improve over time. It is still in a situation where we're doing, one-offs and finding, things that work and, publishing it, but not yet where it's at, a state where it can be engineered. And I would like to view this work as a step in that direction, because one can plug in these models that we talk about into various models here with good effect. And with that, I will thank you for your attention and happy to take any questions.
Okay, excellent. I would like to ask the participants to unmute themselves so that we can thank Gunnar with some applause. Thank you all. So please remember to mute themselves so that we don't get your echoes. And now we go into the question and answer part of the talk. So we have a question in the chat before we take questions from the audience. So Gunnar, Andrea asks, could you explain again how pictures represent the weights of the CNN? So how the 3x3 patches are related to the...
Oh yeah, okay, let's see, let's go back here. Yeah, so you mean how do I get the, yeah. So let's go back to this situation all the way at the beginning. Yeah, right here. So here's the thing. If I take, say, this grid here and this grid, there's a convolutional condition, which I spoke about, which says that actually each one of these, this one and this one corresponds to a single 9 vector. So because you have these, every node is connected to its nearest neighbors, to its 9 nearest neighbors in the grid. And so what I have then is I have a number, attached to each point in a 3x3 grid. So those weight vectors are then vectors with the coordinates arranged in a grid. On the other hand, in images, I also have 3x3 arrays of pixels with grayscale values for each. So the format of the data for the weights and the format for the data for the image patches are identical. And it turns out that it's more than just an analogy like that. What we saw is that that in fact, the weight vectors that occur are exactly the ones that correspond to the patches that are the most frequently occurring.
Okay. Do we have any other questions from the audience? You can go ahead and unmute yourself and ask the question directly. So actually, I have a question, Gunnar. So
Yeah.
So we were seeing in the sort of layers 1 through 13, in these sort of more complicated networks, that you always saw the primary circle come up as you trained. But then those circles are supposed to be combinations of prior circles because we're applying these nonlinearities, correct?
Let's see if maybe you can tell me what are you talking about the 3 circle models? I'm sorry.
So so you show these example where you show the 13 layers.
Oh yes, yes. I understand.
Exactly.
Yeah, I got you.
And
That's right.
But then the circles we're seeing, so the later networks are actually combinations of features we're seeing at prior networks. So do you have a sense of what those features actually are? They look like,
you can, So if you look at layer 7, for example, right? So what that means is it's not that we're thinking of them as combinations. We're thinking of it as just, it's a bigger feature space, which contains, the primary circle, but then contains, it finds that it needs to incorporate crossings and bullseyes. And so it's built a space which includes both the primary circle stuff as well as those bullseyes. Now, yes, those happen to be linear combinations of those other features, but we don't think of them that way necessarily because we're not going to include, all possible linear combinations. It's just these ones that occur. So I would think of it more as sets, bigger spaces rather than, as linear combinations.
Hmm. Yeah, because I guess the difficulty in putting together the sort of understanding of the entire network is not only understanding the layers themselves, but how the activation function and the linear combinations play a role.
Oh,
so, yeah.
That's certainly true too. Absolutely, absolutely. But what I would say here is that if you look at these things, you can see there's sort of a correspondence. If you look at 6, which looks mostly like a primary circle one, you could draw a network which would connect only the boundary, connect only that to only the things in the boundary in layer 7, or the things in that primary circle. So yes, I would agree with you. I think there's a lot to be understood about the relationship between the layers, and that's a great subject for future research. But just to have the fact that you have geometry going on inside, that each layer has a geometric structure, is actually very powerful, because it does allow you these sparsifications, but also it allows you transparency. Because what it means is that you can, when you've got something arranged in a geometry like that, you can view it, activation vectors as functions on there. And so you can see how they color this geometry.
Yeah. Okay. Jesus, so we're now on the dot. So.
Yep. But there is another question on the chat by Benjamin.
I missed
I want to read it.
Okay.
Yeah, go ahead.
How does the accuracy of your machine learning methods, for example, identifying video actions, compare with human, and indeed moved, compared with human accuracy at marketing the same identifications?
Yeah, we haven't done independent tests of that, to tell you the truth. What we found, for example, we've looked at some data done by some, on echocardiograms, where they're attempting to estimate something called ejection fraction, where they seem to do quite well with respect to humans, on diagnosis and so on. In general, you'll find there's a lot of studies, and it's very much dependent on the domain area. So for example, there's a notion of digital pathology now, where you're trying to, diagnose based on deep learning these very high resolution images. And that, and they're doing quite well. That would be a whole big area to attempt to summarize where is it going well and where is it not. But the answer is that there are many situations where one can achieve, something quite as good as or even better than human accuracy.
All right. I think we can stop the recording, but I'm going to keep reading some questions from people in the chat. So Oscar, if you